Okay, so I really want to upload this latest version of the relativistic slide rule, because I've made a lot of interesting updates and things, and interesting interpretations. So that's the new shape of it. I've given up on the superposition, so I've just simply separated it out so that you got a relativistic slide rule above and another one below, and you can imagine it's rotating around that central point, and that would be to do with cosmological objects anyway. That's how it is. And of course that's the what it looks like expanded. Here b equals 1, and coming back to that, b equals the square root of 0.5, and then back to b equals 0. Okay, so let's go back up to 0.6. Get rid of that again. Nothing's changed there, but now that sits nicely in the right spot, which is good. And then we got Einstein's light clock and Lorentz's light clock. So both points of view are just as valid. You can either use time dilation or length contraction. So Lorentz used length contraction, that's the Lorentz transform, and then Einstein preferred to use time dilation, so his light clock's going that way. And then that's Einstein's calculations there for his light clock. And then I've got this Ehrenfest paradox, which led Einstein to come up with the hyperbolic geometry that he needed for general relativity. But here I'm just saying that that's the A's inertial reference frame, and then say that the disk starts whizzing around, then A is going to perceive this distance of 0.75 between A dashed and A, that distance to become contracted due to Lorentz contraction. That would be so I would see it then as 0.6 instead of 0.75, which is that yellow dot, whereas that's not going to work out for a rotating solid disk unless the entire disk contracts, which means you have to have length contraction along that direction, which is not supposed to happen. Whereas Bob's point of view, he's whizzing around with the disk. He's going to say, the length of my ruler hasn't changed, but of course it's increased by gamma according to A in his not moving frame, and therefore his disk must have increased from his point of view. So you've got this superposition, and that's the paradox. They can't both be true, or can they? Or maybe they can both be true if that superposition collapses when it comes to an event. So a relativistic frame shift equals an electromagnetic phase shift which will collapse at an event. No, that's what I wrote there anyway. Can't even remember why I wrote that now. Who cares? So anyway, that's the paradox basically. And but of course, when it comes to them coming together, that superposition disappears, and they can agree on an event there. So that's the Ehrenfest paradox. Refraction. Yeah. What really happens in refraction is that you get a phase shift, so that the light, which is like that, then it gets shifted back by the oscillating electrons in the material. So you take slices through the material, and then there's a phase shift back each time due to the electrons wiggling slightly behind in phase, and that's the real reason for refraction. Negative phase shift on incident wave due to oscillating electron wave interference. Okay. Things changed there. I've got an incident ray. I've got a transmitted ray. That's the oops. Yeah, that's the material water at the moment, 0.6. And then I've got a diffraction grating, so I need to go to 0.9 because now that's what it looks like. So it's clear that little d is gamma. So if I want to make 1 is the wavelength, it's a constant. Then if I want to calculate this this angle here, then let's say I choose a b value of that, about 0.96, then I find out the gamma is 4, so 4 times the wavelength, and I find that the difference, the refraction angle, is 14.47. That's a constant in the wavelength 1. And the holographic principle, this is the angle now. It's bigger. In fact, that would be the maximum angle where you can actually perceive that object. So a smaller d value, which is the gamma, a smaller gamma, it means a higher resolution. So if the photographic film has got a ability for a higher resolution, you can get a smaller gamma, and then you can get a bigger viewing angle. And currently I've got it at 60 degrees, so that means looking in on this photographic film at a 60 degree angle from the normal. he's able to see that object. And then I've got Euclidean geometry. Now that would be Alice's path, and that would be Bob's path, and that's the spacetime PBS. They show the thing. Now notice that my angle of now for Bob, is not the same. And why is that? Well, it's because I'm not using hyperbolic geometry. If I was using hyperbolic geometry, I would go for that, and that actually does match. That line there actually does match, and he's at 0.5. B is 0.5 at the moment, so you can see it matches, and that's the reason why Sabin-Hossenfelder reckons that proper acceleration is the reason, because the distance between there and there is actually proper acceleration. And maybe I could make that clearer by going to a 0.6, and you can see that that's the time that's missed out on by B is actually 2 times the proper acceleration for a return trip. But I don't agree, because when I try to do my calculations for the twin paradox, I find that 0.64 is the amount of time that's going to pass for Alice from Bob's point of view at that B value. So that's the line of simultaneity. These are the lines of simultaneity according to Bob, and I'm going to show that the lines of simultaneity according to Alice is not straight across. This is Euclidean geometry, remember. It's actually that, and so you see they've got different lines of simultaneity, but it's Euclidean. Okay, so according to me, that A primed is entangled with B primed, and because they're on the same line of simultaneity according to Alice, that one, whereas this is the line of simultaneity according to Bob. A and B are on the same line of simultaneity according to Bob, and I'll demonstrate why I believe in that later. Acceleration, it's all cool. That's how you calculate the actual distance travelled by Bob under constant acceleration. So this is still all special relativity, but if we take the example of him getting to a maximum velocity of that, then you find that he will travel. Of course, when he gets halfway, he turns the ship around and continues accelerating, but now it's a deceleration because he's turned around 180 degrees. So he's going to get 4.2 light years doing that. But Alice's proper time would be 5.8 light years. Bob's proper time would be 3.52 light years. Here's the kinetic energy. Notice that it's gamma minus 1 is the radius of the circle. that's the ratio of their times, about 0.6 roughly. But the radius of that circle, that black circle, that's how you calculate the distance travelled. It's as if Bob goes from this little circle, travels out, then comes back and lands on this big circle, which is Alpha Centauri. So it's gone from Earth, and the surface of Earth, to the surface of Alpha Centauri, and he's travelled that radius out and then that radius back. So that's a nice geometrical image for that. So forgetting about twin paradox, I've got anyons. Let's get back to a smaller number. Oops, 0.6. Before collapse, the charge is called an enyon because it can have any charge at all. And if you look at collapse, you see the two charges meet there. It's the speed of light, so that could be a photon there. And then collapsing this way, you get a charged particle. It's exactly -1 and +1 antiparticle. That could be an antiparticle, maybe. Don't know, that's a speculation. But then I've got collapse of the wave function. And this is interesting, because that's the wave function. And let me put Euclidean geometry back in. And now, if those two collapse, the probability of them collapsing is actually the probability of their lines of simultaneity becoming the same, meeting. Of course, momentum is conserved, but so let's get a recognizable p-value. So we're looking at the probability of that collapsing to that horizontal, because my complex plane there, you can see that I is at the top here, and R is the x-axis. So I is the y-axis, R is the x-axis. So this is the probability of a fermion collapsing. Highest resolution, that would be, if you think about the holographic principle, 64% probability of that collapsing at that. And this one's a speculation about collapsing the other way, a 36% probability, and that singularity. I'm speculating it could actually be the self or consciousness, a conscious event maybe. And then bosons, notice you get rid of the half. The cosine doesn't contain, it's not a half inside there, whereas this calculation there's a half inside there, so that's a fermion. That's a boson reflection, where you can calculate it with a little b, and it's transmission. And that's about it. I could put a wave function in there if you like. That's my idea of the wave function. Or if you want to not believe in Fermion mechanics, then you could square the modulus, and in which case there's a probability that it will either go through one, goes through both slits in that case. But because this point here I've got B primed, it's just, it doesn't actually have any mass of its own. Everything is in the field, so I'm more inclined just to believe in Fermion mechanics, and then I don't need to square the modulus. In other words, I'm saying it's gone that way in this case, where it's gone that way. notice that if that is consciousness, that when you get collapsed this way, you get a high resolution world, and no consciousness, just a high resolution world. And if I go the other way, notice that they're orthogonal at about that point there. Notice that these two are orthogonal, which is at the speed of light. Use that orthogonal business. But if you carry on, you can see the wave function doesn't disappear, it actually expands, and this is the lowest resolution where you've only got consciousness, but you're not conscious of anything at all.